In this video, we're going to cover how to solve simultaneous equations. We're going to cover what are simultaneous equations, and then we'll have a look at all the ways in which simultaneous equations are used in the exam. For those already familiar with simultaneous equations, here's what's on the agenda. The video is fully timestamped, so feel free to jump around to whatever suits your interests. Otherwise, let's get right into it. Put simply, simultaneous equations are a set of related expressions. The most common application of simultaneous equations is to find the intersection point of two different lines. Here we have two linear equations which intersect at a point. To find this point, we use a strategy called substitution. The first equation tells us that y is given by 2x plus 3, and the second equation tells us that y is given by negative x plus 1. If two equations intersect, that means that both equations will share the same x and y value at that point of intersection. This means that the y in the first equation will be the same as the y in the second equation, hence we can equate those two expressions. From here, it's simply a matter of solving for x, which in this case gives us x equals negative 2, 1, 3. But we're not done yet. We found the x coordinate of the intercept, but we still need to find the corresponding y coordinate. And we do that by subbing in our result for the x-intercept into any of the original equations. It doesn't matter which one we choose, because as we said before, both equations will have the same x and y value at the point of intersection. So really you just pick the one that has the least complexity in it. Regardless of which equation you picked, after you substitute our value for x, you're going to get the result y equals 5 on 3. Putting our solution together gives us the coordinate negative 2 on 3, 5 on 3. And that's about where you expect the intersection point to be when you look at the graph. So if we're doing that in an exam situation, you can be fairly confident that your result is correct because it's roughly where you expect it to be. Now, let's step up the complexity. In your exam, you may be given a set of simultaneous equations with a third variable. This variable is often called the parameter. In this case, there are two more scenarios that you could potentially be asked to solve for. In the first example, we solve for the case where there is only one solution, where the lines intersect at a single point. But when you add a third variable, the parameter, there are two more cases that could come up. One would be for no solutions, and the other could be where there are infinite solutions. If there are no solutions to the set of simultaneous equations, it means that both lines will never intersect. And this can only happen if both lines have the same gradient, but different vertical translations. Our task is to solve for k such that both of those conditions are met. Suppose we have this set of simultaneous equations. The first thing we should do is rewrite these to be in the form y equals mx plus c, because that's what we're used to. It makes it a lot easier to see what's the gradient and what's the vertical translation. Next, we know that the gradients have to be equal, so let's equate them. After a bit of rearranging, we have a quadratic equation. Now you can solve this quadratic equation however you like. Typically the fastest way is to find the two factors and use null factor law to solve it. Otherwise, if you're struggling to find that under time pressure in your exam, you can always use the quadratic formula, because that will always give you an answer. It doesn't matter what approach you use, you should end up with the result k equals negative 3 and k equals negative 4. But we aren't done yet. These answers tell us where the gradients will be the same, but only one of these results will also give us a different vertical translation. The quickest way to find out is with substitution. So we're going to grab both of our vertical translations and test our values for k in them. If we test k equals negative 4, we're going to see that both vertical translations actually become the same, which is something we don't want. If we test k equals negative 3, we'll see that they're different, which is what we do want. Hence the answer will be k equals negative 3. Solving for infinite solutions isn't much different to when we solve for no solutions. In the case of infinite solutions, it means that both lines completely overlap. That means that equation 1 is the same thing as equation 2. This means that we want the same gradient and the same vertical translation. In fact, we already found the answer to this previously. When we substituted k equals negative 3 into the vertical translations, we found that they actually became the same. So, k equals negative 3 gives us the same vertical translations as well as the same gradient, which is what we need for infinite solutions. So the answer for this question is going to be k equals negative 3. You can still solve for one solution if there are three variables. The only condition you have to look for is where the gradients are different. The vertical translation is irrelevant. If two straight lines have different gradients, then they're always going to intersect at some point. The good news is, again, we already solved this. We found that the gradients are the same for k equals negative 3 and k equals negative 4. So if the gradients are the same for those values, then the gradients must therefore be different for all other values. Thus, our answer becomes all real numbers excluding k equals -3 and k equals -4. To summarise, solving for no solutions means that we want the same gradient but different vertical translations. To solve for infinite solutions, we want both gradients and both vertical translations to be the same. And lastly, if you just want to find one solution, then all you have to do is find where the gradients are different. The last thing you might be asked to do in your exam is to find the general solution to a set of simultaneous equations. This will usually be given to you as a tech-active multi-choice question like this one is here. You'll notice that there's actually a fourth variable in the solution sets. This is often called the parameter, and usually the Greek letter lambda is used for this. The parameter is only there so we can express all of our solutions in terms of a single variable, and that variable is either assigned to x, y, or z. In a multi-choice question, it can be any of those variables. So that's why the first thing to do when it comes to these questions is to group all of the solutions in terms of lambda. We can see that answers A and C use y as lambda. We can also see that answers B and E use x as lambda. And finally, we have answer D, which uses z as lambda. Now that we've grouped the solutions like this, we can start to use the CAS to solve it. These kinds of questions are best solved with the guess and check method. We can do this by setting up the simultaneous equations on the CAS, which you can find under menu 371 on the TI Inspire. Set the number of equations to 3 and define the variables as per the question, which in this case is x, y, and z. The first two equations are just going to be the original equations that we got from the question. Our third equation is going to be chosen using trial and error, using the groups that we found in the first step. Let's say that we want to test z equals lambda. Well, our third equation is just going to be z equals lambda. On the CAS I've used k because the actual letter doesn't matter. Once you hit enter, you're going to get a set of solutions. All you have to do from here is compare that against the multi-choice answers. If you get a match, great. In this case we don't, so we're going to test the next bucket of solutions. So this time we're going to try x equals k. Again, we're going to find that the solutions don't match, so we're going to finally try y equals k. At first glance, it may not look like we got a match. The x and the y expressions are identical, but the z isn't. All it takes is a bit of rearrangement to get it to become a perfect match. The CAS is likely to format your answers differently to how it's expressed in the multi-choice, so it's always good to go back and rearrange some of those earlier expressions if you didn't get any perfect matches the first time around. Okay, so now we have two possible answers, A and C. The only difference between these two answers is the restriction on lambda. In A, lambda can only be an integer, whereas in C, lambda can be any real number. Solutions to simultaneous equations aren't restricted to just integers. They can be any real number. Hence, C is the only correct answer. It may be possible that you're asked a tech-free version of this kind of question. I haven't seen it happen in any of the trial exams, but the textbooks do give you some guidance on this, so it's worth covering just in case. This one here came from the Cambridge textbook. First, we're told to subtract the second equation from the first equation. Easy enough. We can also rearrange that result so we can get y in terms of z. Next, we're told to let z equal lambda, and then solve the set of simultaneous equations all in terms of lambda. So, the first thing we're going to do is go through our equations, and everywhere that we see z, we're going to replace with lambda. And by doing that, we've already solved the first two variables of the simultaneous equations. We know that z equals lambda, and we also know that y equals -2 plus 4 lambda. All we need to do now is find x, which we can do using substitution with any of our original equations. The easiest one to use is the second equation, so let's start there. All we have to do is sub in our result for y into that equation, and then rearrange until we get x on its own. And just like that, we have a set of solutions that are all in terms of lambda. If you found this video helpful and would like to see more, I actually have written versions of these lectures available for free on my website. Just click the link in the description below and it will take you to my website. Just scroll down a little and click this heading to get access. No opt-in required, free of charge.